Okay, hoping that you can hear me okay in New York. Not hearing any objections. So
we can hear you.
Okay, great. Then let's roll along. So I'd like to begin by talking a little bit more about Black's formula, and in particular talking about replication and some of the ideas that are on the homework. Both there is the fourth homework and the fifth homework, and I'd like to talk about some of the ideas that you see on those homeworks. And then in the second, or maybe the second two-thirds of this evening, I will introduce foreign exchange models. And we'll see another chance where we change the numeraire and change the measure. So let me remind you of Black's formula. So Black's formula, we have an S of t, which is a price of some asset, and this is denominated in dollars. And we have a zero coupon bond. It pays 1 at maturity capital T, and it is also denominated in dollars. And we do not assume a constant interest rate. Black's formula will work if the interest rate is constant, but you do not need to assume that. So the interest rate is typically some random time varying thing. And what's basically going on is we're going to price everything not in dollars, but in units of bond. And so, for example, if we take the risky asset S and price it in units of bond, so the price of S in units of B, this is actually the forward price at time little t for delivery of 1 unit of S at time capital T. And the assumption that we're going to make is that the forward price has a constant volatility. So here is the assumption behind Black's formula, which we will relax this evening. So the forward price has a constant volatility, which I'll call sigma. And that means in particular that if you write down the differential of the forward price, you'll get sigma, and then you'll get the forward price, and then you'll get the differential of a Brownian motion, and we get to choose which Brownian motion we want. And of course the Brownian motion we would like to choose is the forward Brownian motion, the one we've called W capital T, because that's the one that makes, when we're working under the probability measure, the forward measure, that makes this be a Brownian motion, then the forward price is a martingale, and right, it's a quotient of martingales, the discounted S over discounted B, and when we switch to the forward measure, it's a martingale, and we don't have a dt term, and so that makes our equation simple to write it here with dw capital T rather than dw tilde. And then the Black's formula says, so we want to price a call. Paying S of capital T minus K, positive part, and this is in dollars at T. And the dollar price of the call at T is, and then we plug into the risk neutral pricing formula. I'll call this C sub t. This is a random process because I'm going to let t vary tonight. And so we're just looking at the call price at time little t. The little t, of course, is between time 0 and the expiration date of the call. And the risk neutral pricing formula says we do 1 over d of little t, expected value under the risk neutral measure, d of capital T, S of capital T minus K, positive part conditioned on F of little t. Right? And I haven't written down D of capital T, D of little t, but it's what it always is. It's the discount process. Now, we want to change the measure because that'll make the pricing easier. And to change the measure, we have to think about how do we do that. And of course, we're using bonds as the numeraire. And so the Radon-Nikodym derivative process that we want it's an M, derivative process is, and I said when you change the numeraire, we're taking bonds as the numeraire. The way I remember it is that I essentially want to take the numeraire as the Radon-Nikodym derivative process, but I need a martingale, and that's not a martingale, so I will discount it. So now it's a martingale, and I need it to start at 1, but if you plug in little t equals 0, this is a 1, and this is b of 0 capital T, which is not a 1 typically, and so I'll divide by the initial bond price, and I'll use that as my Radon-Nikodym derivative process. And that will change us to the forward measure. So this changes us from the risk-neutral measure to the forward measure, and we'll do that on the next page. So C of T is, and I want to write this formula down again, but what I would like to see is my Radon-Nikodym derivative show up. And you recall that when you want to change a conditional expected value from one measure to another, you multiply by the Radon-Nikodym derivative at the time of pricing at the capital T. So in here, I would like to see a D of capital T, B of capital T over B of 0 capital T. That's this Radon-Nikodym derivative at the time of pricing. And then I still have the random variable whose expectation I'm taking. And then in the front, I want to multiply the reciprocal of this at the time of conditioning. So that would be B of 0 capital T over D of capital T, D of little t, B of little t capital T. But I don't get to just write whatever I want. Whatever I write has to agree with what I already had. And if you look at this for just a moment, it almost does agree. This is a 1, so that's not really there. And this term would cancel this term. And so what I have inside the expected value is just D of capital T, like I had there. What I have outside the expected value, well, I have this D of little t in the denominator like I have here, but there's one extra term. And so I have to cancel that as well. So let me put it, if I can squeeze it in right here. Let me do it this way. I have to put that in right there. When I go to the next line, then I have that last term that I put in, and then everything else is about changing the conditional expected value from the risk-neutral measure to the forward measure. And so what I'm going to do is get a conditional expected value under the forward measure, and this random variable that's being computed here, whose conditional expected value is being computed, is still there. I don't remember the exact lemma number. Lemma 5.2.2 perhaps. I'll put a question mark. I think that's the lemma. But if you look in the book, we're using that. It tells us how to change a conditional expected value using the Radon-Nikodym derivative at the time of the measurability of the random variable we're trying to take a conditional expected value of, and the reciprocal of the Radon-Nikodym derivative process at the time of the conditioning, which is little t in this case. And that will change this conditional expected value to the forward measure conditional expected value. And then once we get to that point, we observe that if capital T, the price of the underlying is the same as the forward price of the underlying. We're computing under the forward measure. If we write the evolution of the forward price under the forward measure, it's a geometric Brownian motion, and it's as if the interest rate is a zero. There's no dt term here. There's no r times forward price dt. And so what we're going to get out of this is a Black-Scholes formula with an r as if the r were zero, and then we get the bond price multiplying it. So what we'll get here is b of little t, capital T, and then I'm going to get the forward price, little t, capital T, and I'll get an n of d plus term, and then I'll get a minus k, and I'll get an n of d minus term, and the d plus and d minus here are 1 over sigma, that's the volatility of the forward price, and the square root of the time till expiration, cap T minus little t, because we're pricing at little t, and then the log of the forward price over the strike price plus or minus 1/2 sigma squared cap T minus little t. Okay, let me pause here and see. So this is an argument that we've used before, although when we used it last time we weren't conditioning. We were just taking unconditional expected values. So I've raised the stakes on you just a little bit by doing it with a conditional expected value. Let me pause here and see if there's any question about what I just did. So it builds on things that we've talked about previously. How do we change the measure, and what is the forward Brownian motion? Any questions? Everybody happy? Or as happy as you're going to be? Okay, so let me observe now that this thing d plus and minus becomes a process in little t, right? This changes with little t, and also because the forward price is random, it's a function of omega. This d plus minus thing is a function of omega, and so to emphasize that, I'll write here d plus minus of little t. It's itself a random process. So this is a random process as well. We can come back up here to our formula for C of t. And when we look at this term here, when you multiply a bond price times a forward price, if you multiply a bond price times a forward price, you'll just get the S of t, the numerator. And so this product right here gives us S of t, n of d plus, and here I will emphasize that d plus is itself a random process, minus k n of d minus of t, and this bond price distributes through and sits over here. And this suggests a replicating portfolio. If you want to hold a portfolio that is always equal to the value of the call price, what you could do is go long n of d plus of little t shares of S, and go short k n of d minus of the bonds. Of the T bonds. If you go back and think about the case of a constant interest rate, and this covers the case of a constant interest rate, and in the case of a constant interest rate, the bond prices are easy to compute. They're just one discounted from capital T back to little t at the interest rate, so you know what those bond prices are. You could check and see that this is exactly how the replicating portfolio works in the Black-Scholes setting with a constant interest rate. And so this seems like a pretty good idea. And the question is, would that work here as well in the case of the non-constant interest rate? And so what is it that we have to answer to figure out whether that works or not? And it's the issue of self-financing. So remember how we get replicating portfolios to work. We take discounted call prices and differentiate them, and we take discounted portfolios and differentiate them, and we set the two equal. Now, in this case, we don't have to think about discounting. We can just take the differential as it sits here and see what happens. And if I take the differential of C of t, let me leave the t's out just so it doesn't fill up the whole page. If I take the differential of C of t, I first of all see a product, right? Two random processes here. And Ito's formula says you'll get S times the differential n of d plus, and then you'll get the differential n of d plus, then you'll get n of d plus times the differential of S, and then you'll get the differential of S times the differential of n of d plus, right? That's Ito's product rule applied to this term. And then you have to apply Ito's product rule to this term, and you get B. Let's see, I'm leaving the arguments out. So just B times the differential. I'm going to keep the K with the n of d minus. And then you get minus the other way around, K n of d minus times the differential of B. And then you get minus the product of the differentials, d K n of d minus dB. How about the portfolio that I'm describing? So the evolution of a portfolio described on page 2. Okay, it's the one that's long this many shares of stock and short this many bonds. What will happen if we move forward in time and we're holding that position? Well, if we're long this many shares of stock and the stock price changes, we'll get n of d plus ds. And if we're short this many bonds and the bond price changes, we'll get minus k n of d minus dB, and that's all. When we have been doing this in the past, we've had the position, the delta that you're holding in the underline, the delta that you're holding in the underline, your position times the differential of the stock price, and then you've had a term that keeps track of the cash. You figure out how much, whatever's not in the stock is in cash, and that's growing at the risk-free rate. And if you chase it down, this is that term right here, because this amount right here is the amount that's going to be in the bond, and then you multiply it by the change of the price of the bond, and that's all you get. If you write it down in discrete time and pass to the limit, that's the whole story on the portfolio. And so these two differentials are going to match if and only if these four terms are 0. And that's what we need in order to say the portfolio is self-financing. What I'm saying here is that when I look at the call price and I see this, I see that if I hold at time t, I hold this portfolio, then the value of my portfolio will be exactly the value of the call price. But what I'm worried about is if I go a little bit forward in time, and now I have to change my position in the stock and I have to change my position in the bond. Suppose I have to increase in the stock and reduce in the bond. Will selling the bond generate enough cash to buy the stock that I need in order to maintain this position? Right? That's the issue that I'm worried about. And what I'm saying here is that in my portfolio, the only changes in the value of the portfolio are due to changes in the stock price and changes in the bond price, not due to anything funny that I'm doing when I'm rebalancing. And this equation here says that when you rebalance, you don't put any money in, you don't take any money out. I don't know if Scott did this with you in discrete time or not. If you write this equation, the discrete time analog of this equation down, it says really when you rebalance, you're not putting any money in and you're not taking any money out. Have you seen that derivation for this equation? This thing being equal to 0? I see Catherine says, no, I haven't seen it. Okay. Anyone else?
I think it's in the homework.
Okay, so why don't we take just a moment and let me write this equation in discrete time. What would this look like? So it would be a little easier on the I if I call n of d plus of t, let me call that delta 1 of t. That's my position in stock. And minus k n of d minus of t, let me call that delta 2 of t. That's my position in the bond. And the reason I'm changing the notation is just because it's shorter to write delta 1 and delta 2 than this stuff. And the portfolio equation we're looking at there says delta 1 ds plus ds d delta 1 plus delta 2 dB plus d delta 2 dB is 0, right? That's the equation that I'm writing down. What would that look like in discrete time? Well, suppose we're sitting at time tk. This would say delta 1 of tk, s of tk plus 1 minus s of tk plus d delta 1. So that would be delta 1 of tk plus 1 minus delta 1 of tk times s of tk plus 1 minus s of tk. Okay, so that's the ds d delta 1 term. This term would be delta 2 of tk, and then bond price, I'll leave the capital T off and just write bond price at time tk plus 1 minus bond price at tk. This is the capital T maturity bond. And then here's a product of differentials. So this would be delta 2 of tk plus 1 minus delta 2 of tk, b of tk plus 1 minus b of tk.
So, in the first equation, for dx of t, we have a n of d plus into ds. So, means we don't need to have that term in the sum.
So let's see. In the first equation, I'm sorry, say that again.
Dx of t is n of d plus into ds minus k of n of d minus into db.
Yes.
We want dc to be exactly equal to this. So the remaining 4 terms sum should be 0, but n of d plus we included that also.
And we also included knd minus db as well. I just think that the number, the first the two terms you've left out should be included, and the second and the third terms you've included should be excluded.
Have I messed that up? So we want this is our position in the stock and then change in the stock. So here's our position in the stock and change in the stock. And here's the change in the stock times the change in position. So that would be this term. And here's our position in bond. The minus sign is part of the delta 2. So here's our position in bond times the change in the bond price. So there's position in bond times the change in the bond price. And then here's our change in position in bond. That's the delta 2 tk plus 1 minus delta 2 of tk. And then change of the bond price, that's this one. So,
yeah, but are those the terms that you really want to set to 0 if you want dc to match dx? Because in dx you have n.
Oh, I see what you're saying. I see what you're saying, yes. I'm sorry. These are the two terms. Ah, good. These are the two terms I want to keep, this one and this one, right? Because those are the ones in dx, right? And these are the terms I want to go away. Okay, so I should start again. Okay. So what we should have here is S d delta 1, and what we should have here is B d delta 2, right? Good. That shows that you're really paying attention. Okay, these are the 4 terms that I want to go away. Okay, so now I have to write this whole mess down again. So I have S of tk, delta of tk plus 1 minus delta of tk And then I have S of tk plus 1 minus S of tk. And this is the delta 1. And I have delta 1 of tk plus 1 minus delta 1 of tk. And then I have B of tk, delta 2 of tk plus 1 minus delta 2 of tk. And then the product of differentials would be delta 2 of tk plus 1 minus delta 2 of tk, B of tk plus 1 minus B of tk, and I want that to be a 0. These two terms will combine. They have a common factor, which is the differential of the delta 1. And so I can add them together, and the S of tk will cancel the S of tk. And I'll get S of tk plus 1, delta of tk plus 1 minus delta of tk. And these two have a common factor. It's the differential of delta 2. And this B of tk will cancel this minus B of tk. And so I have B of tk plus 1, delta 2, this is a delta 1, and this is a delta 2 of tk plus 1 minus delta 2 of tk equals 0. So how is this working? If we're working in discrete time, at this point tk, we take positions delta 1 of tk and delta 2 of tk, and then we hold them until time tk plus 1, and we get whatever profit and loss is associated with that. We'll get these two terms, right? Our position in stock times the change in the stock price, our position in bond times the change in the bond price. That will go into our portfolio, change the value of our portfolio, and then when we get up here, we're still holding our positions delta 1 of tk, and we want to replace that by a new position, delta 1 of tk plus 1, and we're still holding our position delta 2 of tk. We want to replace that by a new position, delta 2 of tk plus 1, so we're going to trade in order to do that. And this equation at the top of the page says that that trading is done at 0 cost. The change that we make in our position in the stock times the stock price plus the change that we make in the position in the bond times the bond price at time tk plus 1 adds up to 0. So it means that one of these increments, the differential of delta 1, if it's positive, the other one has to be negative. If you're buying stock, you're selling bond. If you're buying bond, you're selling stock in exactly the right proportions so that this trading finances itself. That's the self-financing condition. And it boils down to a sum of 4 differentials, and I think it's these 4 differentials now that you've corrected me, equals 0. Okay, so to show that this portfolio works that we're proposing here, this portfolio here, that's long delta n of d plus of t shares of stock and short k n of d minus of t shares of bond, you have to check. So self-financing condition in continuous time. Let me see if I can get it now. It's S dn plus dn of d plus. That's this one. ds dn plus. ds dn of d plus. Minus this. Minus b differential k n of d minus. And this one, the product of differentials minus db dk n of d minus equals 0. And it does work, and I could give that to you for homework, but if I did, you would have to work pretty hard because the formulas for d plus and d minus sit right here. and you're going to have to take their differentials, so you'll have to differentiate with respect to t. And in addition, you have this forward price sitting inside a logarithm, and the forward price has a stochastic differential. Right here's the differential of the forward price. And so you'll have to use Ito's formula, and you'll have to work a little bit to check that this equation is true. I am going to give you this for homework, but I'm going to make it a little simpler first. In fact, I've already given it to you for homework. But here, let's make it a little simpler. And what I'd like to do is price everything in units of bonds rather than dollars, because that'll reduce this from 4 terms that you have to compute to 3. So I'm going to price in bonds rather than dollars. So price what? Here's the equation. It's this equation right here for the price of the call. So on the left-hand side, I'm going to look not at the price of the call in dollars, but the price of the call in bonds. And that's really the forward price of the call. And on the right-hand side, I divide by bonds, and what I'm left with is n of d plus and minus k n of d minus. What's the differential of this portfolio? Now there's one term that I want. Let me get it right. So that will be n of d plus times the differential of the forward price of the stock. And there are 3 terms that I don't want. So what else is there? Well, the product rule says you have to also get the forward price times the differential of n of d plus, and you have to get the product of the differentials for the differential of that product. Here we don't have a product. Here we have simply minus k times the differential n of d minus. And let's think about a replicating portfolio. I'll call it y of t. It's going to hold at each time n of d plus of the underlying asset. And when the price of the asset moves, we get the profit or loss associated with that. But I'm pricing the asset not in dollars, but in bonds. This is the price of the asset in bonds. So this is priced in bonds, denominated in bonds. And I'm also going to be short k n of d minus bonds. What do I write down here to reflect that? When we had our dx, this one's priced in dollars. I had the position in the stock, that's these term, and then I had the differential of the dollar price of the stock. Here I write the differential of the bond price of the stock. And then I had k n of d minus bonds times the differential of the bond price. This is the dollar price of the bonds. What do I do now? So you need this for one of your homeworks. What's the next term? What's the bond price of the bond? 1. What's the differential of 1? 0. So there's nothing else. Right? We're done. Okay? It's like having a 0 interest rate. And I have this asset whose price is always 1. Right? So that's like having a bank account. It's like having a bank account at Citizens Bank these days. 0 interest, right? You put 1 in, you come back 6 months later, you still have 1. And so it's like having a 0 interest rate. So when we price in bonds, we only get this one term. And so what we want to check self-financing is to check that these 3 terms add up to 0. That's the first homework problem on homework set 5, is to just do that calculation. While I'm on the subject, I'd like to make a remark about homework 4. So in homework 4, exercise 1, part 2, you construct a portfolio and it's going to hold delta 1 shares of a risky asset S. It's going to hold delta 2 calls priced at C of t and S of t. And both S and C are denominated in bonds, so these are the prices in bonds, not in dollars. And to finance this, by trading in bonds, and so d of t will be delta 1 of t, and where I'm writing ds of t now, I really should be writing d forward price of s, but it's common practice if forward prices are the only prices in your model just to call them s. And so that's what happens in this in all of homework 4, in fact. Forward prices are the only prices, and we call them s rather than using this notation. And then we hold delta 2 calls, and we get the profit or loss associated with that. And then we could figure out how many bonds we hold. Right? How would I do that? Well, I would say I'd figure out X is the total portfolio value. I've got this many shares of stock, a risky asset, I can compute the value of that. I've got this many calls, I can compute the value of that. I subtract it off of X, and that tells me how many bonds that I hold. Right? Everything's priced in bonds. And I'm going to finance this by trading in bonds, so there will be some number of bonds. In fact, maybe we could write it down. So it's going to be the portfolio total value in bonds is that. I hold this many shares of the asset, and its price in bonds is this. I hold this many calls, and the call price in bonds is this. And then I multiply it by the differential of 1. Right? Because this goes into bonds, and the price of bonds in bonds is 1. So this gets multiplied by the differential of the number 1, which is a 0, and so the whole thing is gone. And so you only see the first 2 terms in that exercise. Okay, just wanted to be sure you got that set up right. Let me see if we're okay on this point. Question?
Yeah, Professor, when we try to hedge in this case, like, are we supposed to use the partial of the f function mentioned in this problem?
Yes. So when you work out your hedge, the hedge is going to be written down in terms of the partial derivatives of the call price and the partial derivative. There's another derivative security in this problem. If you haven't looked at it, there's another derivative security, and its price is f of t and s of t. And when you create the replicating portfolio, it will involve the partial derivative of f as well as the partial derivative of the c. Okay. So we started out by saying Black's formula assumes constant volatility. What if we have non-constant volatility? With non-constant volatility, you can either be looking at the dollar prices of things and assume that you don't have constant volatility, and then you have to modify the Black-Scholes formula, or you could be looking at the forward prices and assume that you have non-constant volatility and you have to modify Black's formula. They kind of go pretty much the same way. I'm going to choose the second case. So I'm going to do non-constant volatility of forward prices, which messes up Black's formula. So there are a number of things that we can do. The first one I'd like to talk about is local volatility. So the names here are Dupier and a paper by Durham and Connie. Dupier did it for stochastic calculus, so what we're going to do is Dupier's work, and Durham and Connie did it for binomial models. And Dupier is now the director of research at Bloomberg, but he was at BNP Paribas when he did this, and Durham and Connie were at Goldman Sachs. And the problem that they were facing was the following. Suppose you have, let's do a knockout call, and the payoff is something like this. So here's capital T. Here's the initial, we're going to use S for forward prices. Here's the strike price K. We have a call. We'd like to expire in the money, so then we get a payoff. But in addition, there's a barrier here. And if the stock price ever goes above the barrier, then the payoff is 0. So we could have a different path that would do this and end at the same point, and the payoff on this path is 0 because this knocks out when it goes above the barrier. So we have a knockout here. Zero payoff when that happens. The way the industry uses Black's formula is that if you have a call, they say, what volatility would I need to plug into Black's formula so that the formula price is the same as the market price, and they call that the implied volatility, right, implied by the market price. And the implied volatilities differ for different strikes. So for this strike K, I might have an implied volatility of 20%. But if I had a call that was struck, I don't have a call that was struck at B, but if I had a call that was struck at B, and I look in the market, I might discover that its volatility is only 10%. But here I have a derivative security which depends both on levels K and B. So should I use the volatility of 20% for calls struck at K, or should I use the volatility of 10% for calls struck at B? What should I do for the volatility that I put into Black's formula when I'm trying to price this? Well, actually, Black's formula won't give me a price for this, but if you were to look at this model, ds of t is sigma s of t dw of t. Right? And again, I'm writing the formula that we began with in different notation. So this formula, I'm writing S instead of forward price, and I'm writing W instead of W forward. Right? That's the industry practice to drop all that notation. So I can price a knockout barrier option if you tell me what sigma goes here, and we'll do that actually at the end of the course. We'll talk about how would you actually compute the price of a barrier option on a geometric Brownian motion, but you need to know what is the sigma. And what sigma am I supposed to use? Right? I remember Dupere giving a talk in which he phrased it, well, do I use this implied volatility of the strike, or do I use the implied volatility of the barrier and put into here, or do I use something that's in between? And the answer is you use none of those, because volatility has a very different effect in a knockout call than it does in a vanilla call. If you're getting up here close to the barrier, more volatility makes it more likely that this will knock out. And so as the volatility increases, the price of the knockout barrier call goes down, not up. And so things go counterintuitive here. And Dupere said, let's do the following. Let's look for a model not of this form, but a model of this form. So I'll let sigma be a function of t and s of t. So sigma, I'll write it here to emphasize, it's a function of two variables, t and s, a non-random function of two variables. Let's look for a non-random function of two variables so that if I use this model, all the calls that I see, all the vanilla calls that I see are priced correctly by the model. And if I can find this function of two variables that does that, then I'll use this model and price the barrier option. So that was Dupere's idea. So how difficult is it to find that function? So finding the function sigma, a function of t and s. We'll want to define it for all times between initiation and expiration and for all s's positive. So we look in the marketplace and we see quotes for calls. Of various sorts. Strikes and maturities and expirations. We also see quotes for puts. And these imply quotes for calls. Via put-call parity. So what you could think here is you've got different maturities, different expiration dates, so T1, T2, T3, T4, T5. You've got different strikes. And you have quotes at all these expiration dates for all these strikes for call prices. And you interpolate this data smoothly. So fit a smooth function to these data and call it, so these are prices of calls at time 0. They're TJs here. We know what the initial stock is. It's not price is, initial forward price, it's not random. And their strike price is KIs. Okay, but what I'm going to do is not just make it work for TJs and KIs, I'm going to make it work for all Ts and all Ks. So I fit a smooth function to this. And then you did a homework problem, the one that uses the Kolmogorov forward equation. And if you go back and look at your homework problem, it says that if you take the time derivative of this function you'll get 1 sigma squared of capital T and K times K squared times the second derivative with respect to the strike of this function. And you solve for this. And take the square root, and you'll get a sigma. And one of the reasons I insist on not just thinking that the only thing that can go into these processes, into these functions somewhere, right? Here I've written sigma with the stock price sitting as its argument, but I insist that these are functions of real variables, not functions of random variables, and you can put any positive number in there that you like, and here I'm putting in the strike price. So I put in the strike, where is that? Here I put in the strike price, and this is going to determine a function of 2 variables, right? This equation is going to determine a function of 2 variables, and if I take that function and build this model and start pricing using this model, it will get right every one of these call prices that I've calibrated this model on. And what do I mean by use it and use this here? Well, there are 2 ways to do calculations. If I want to now compute the price of a barrier option, and I've got this function of time and S, there are 2 ways to compute prices of barrier options. One way is that you can write down a partial differential equation and solve it for this. It's a little tricky because it's a little bit path dependent, but you can deal with that and write down a partial differential equation and solve it. And the other way is that you can do Monte Carlo. The only difference is when you're doing Monte Carlo is that the sigma now is a function of time and stock price, but that doesn't mess up the Monte Carlo, and then you can price the barrier option that way. Okay, so this was Dupier's idea, and again, Derman and Connie had the same idea and implemented it in a binomial tree where it's actually a lot messier than in stochastic calculus. And you get all the vanilla call prices right, and everybody got really excited. This model calibrates perfectly. Okay, so do you understand what Dupier has done here? Question? Yes.
So, in the market, usually for different strikes, different volatilities. I mean, that's why we get a volatility smile, right?
Right.
So I would assume that for the same strike and all parameters remaining same, one option that has a barrier and another option that does not have a barrier might have like a different volatility, might have different volatilities.
Yes, that's right.
So what's the point of taking volatilities from this analysis and plugging it into this to price barrier options?
So it is correct that if I take this barrier away and look just at the vanilla call, the implied volatility of that, well, I'm not sure what to call the implied volatility of the barrier.
We might not have that volatility in the first place, but just assuming that, I mean, in the market, if somebody had to price a barrier option, they would probably use a different volatility.
Probably they would use a different volatility from the one that's implied for the vanilla call with the strike K. The sigma that comes out of here now is a function of both time and a real variable, right? Which can be either, sometimes it's a stock price, sometimes it's a K, right? It's a function of 2 variables. We're getting a sigma function of 2 variables. It's not an implied volatility for anything, right? It is the volatility that you use in the model in order to get the model to correctly price all of the calls that you've calibrated to. So it's not an implied volatility for any of those calls. It's something different. And you can take this model and you can price a vanilla call and you can back out the implied volatility and you'll see that it's not related to the sigma that went in because the sigma is it's called a volatility surface, right? And it looks like a function of 2 variables. There was maybe a question cooking in New York. I saw the camera start to zoom in. Was there a question? Yes, go ahead. So for now we're not working in reverse. I'm not hearing anything.
Can you hear me?
Yes, I can, Akram.
Come on.
So maybe just try a different. Just try a different microphone.
I was just wondering why the 2 volatilities can be used interchangeably. Because one's a function of strike, the other one's a function of asset price. So how can you use the the function of strike in place of the other one?
Because you did the homework problem. So you did a homework problem, and it said that if you take a model that looks like this, where you have a sigma that's a function of time and stock price, and you price calls in that model, and then you compute the theta. Well, it's not the theta. This is the derivative with respect to the time to maturity, not the current time. So I guess this would be the negative of the theta. And this is not the gamma, because this is a derivative, second derivative with respect to the strike price. But if you do these calculations, the function that you put in pops out right here, but with the strike in place of the stock. And that was the homework problem you did. So I'll throw the question back to you. I mean, it's not intuitively obvious that that should work, but you went through all the details. I hope. The solutions are out there. If you didn't, the solutions are there.
I have a quick question. I still don't understand how are we able to use this function to price barrier options. Like, I could see how you could do implied volatility for vanilla options, but why do we need it for barrier options?
So the reason it was developed was because nobody knew what implied volatility to use for the barrier options. And this at least uses the data for the calls that you have and produces a model that prices correctly all the calls that you have, and then you have a little more faith that that would give you a good price for barrier options. That's more than that, there's nothing to be said. I mean, what is the right price for a barrier option? It's traded over the counter. There's no, there's no quote for it. What is the right price? This produces a number, and it takes into account all the vanillas in the calculation. And in fact, you're using a model that gets all the vanillas right. And so you feel like, okay, it should be getting the barriers pretty close too. Okay, and the other question about how can I take this variable where the stock price goes and put the strike in, again, I will say it's really important to understand that these are just functions of variables, and the variables can be anything. And depending on how you do the math, you discover that sometimes the stock price goes there, and sometimes the strike price goes there, and the math is all in that homework problem. So over time, people became less excited about local volatility, and the problem is with the dynamics. So in many fixed income markets, if you're thinking about implied volatility, so here maybe is the underlying asset price at time 0, and here I'm putting the strike on this axis. So when I'm thinking about calls, so when the strike is above the call, this is out of the money over here. And in over here, when the strike's below the current price. And right here is at the money. And then if you look at the implied volatility, you might see something like this. So here's the implied volatility at the money. Over here you get higher implied vols. Here you get slightly lower, but then it comes back up again. So that's the volatility smile, and the bottom of the smile is usually a little bit to the right of at the money. Let me call it skew and smile. I've actually drawn it poorly because usually the upward piece is not as big as this downward slope, and so mostly you see something that's moving down with a little bit of up here when you get far out of the money. And now what happens? Let's suppose we have done our Dupier model. We have built our implied volatility surface. We've gotten our function of sigma of time and space. And we start pricing our calls. And it works great. This is a different axis. This is time here. And this is, let's see what I want to do. I'm sitting here at time 0, and I set this thing up and I make it work, and it works great. And then I go to time little t here, and I have my function, so I want to put s here. I have a function sigma of u and s. I'll call this axis u. Okay, so it's a function of two variables. It's defined in this region. I move forward a little bit of time. This part of the function is now irrelevant, but I still have the function from time t onward, and I could use that to price from time t onward. And if you do that, you'll get an implied volatility, right? So let me make clear what I'm doing here. So at time t, we have a new stock price. S of t. So I use that initial condition. And the same function, I use this equation, ds of u is sigma of u and s of u dw of u. Use that model to price calls. When I get those call prices, then I can ask, what are the implied volatilities of those calls, right? So the model produces call prices. For each of those prices, I can say, well, what sigma would I have to plug into Black's formula in order to get Black's formula to agree with that? And so I could get the implied volatilities of the model-produced call prices. It turns out that if at time t the stock price moves right, the implied volatility curve moves left. And so what you would see is if the stock price moves right, then it would be, this curve would move left. As if the at the money were over here. It goes the wrong way. And what that says is that once a week passes, you're going to have to recalibrate the model. You're going to have to compute all over again this function sigma of time and stock price. And if you don't do that, or even if you do, the hedges are not going to work very well because the hedges are thinking that the implied volatilities are going one way, and in fact, if you look at the market implied volatilities, they will go with the stock price. When the stock price moves right, the implied volatility curve will move right along with the stock price, but the one that's produced by this model will move left. And for that reason, people have become a lot less enthusiastic about these local volatility models than they were initially. I guess you could argue it's a case of overfitting the data. You get it to price everything right today, and then tomorrow it doesn't look very good. Okay, have I said that clearly enough that you understand what the issue is? Right. That you'll want to recompute fairly frequently. And when you are, the problem with recalibration is that your calibration is giving you a model, and your model is telling you how to hedge. And if you're going to have to recalibrate tomorrow, it says that your hedge may not work because the assumptions that you've built into your model are going to be wrong very soon, and your hedge may be wrong as a consequence of that. And so for pricing, this may make sense, right? And you may still want to use this to quote a price for a barrier option, but you wouldn't want to set up hedges based on the model that comes out of this, this local volatility surface. So we need to talk about other things, but we've been at it for a little more than an hour. So why don't we take a break, and then we'll come back and talk about the SABRE model and the CEV model that have been developed to deal with these kinds of problems. Shall we take 10 minutes? So come back at 5 minutes till. Okay, why don't we reconvene? I apologize for giving you more break than intended. I got into two different conversations in the hallway. Let's talk about SABRE. So first of all, I was rereading the SABRE papers, and discovered that my memory was incorrectly when I was writing the homework. I wrote the homework and said SABRE comes from, the S in SABRE has to do with S for the asset price, what we've been calling S. In fact, it's not. If you go back and look in the original papers, the S in SABRE comes from stochastic. And the others come from alpha, beta, rho, which is really dumb because alpha, beta, and rho are just names that are given to parameters in the model. You could have called them anything. So it's a dumb name, but there it is. We're stuck with it. So what does the SABRE model look like? It says, let's assume that the underlying asset, and again, I'm still working with forward prices, so I'm not going to have any RDT terms, has a volatility sigma of t, which is itself a random process, and then there's S to the beta of t, and then a first Brownian motion, dw1 of t, and then there's a model for the volatility. The sigma of t is a constant nu, sigma of t, dw2 of t, and these Brownian motions are correlated. dw1, dw2 is equal to rho dt. And we're going to start the volatility off at a value alpha. And so we have actually four parameters. We have the initial condition on the volatility, alpha. We have the beta, which is a power on the asset price. We have the rho, which is the correlation. And we have the nu, which is a constant here. And I don't know why nu doesn't get any press in the name, but it's only the alpha, beta, and rho that show up. What are the story on these parameters? 0 is less than beta is less than 1. You can take beta to be 0 and you can take beta to be 1. Even if beta is 1, this is not a geometric Brownian motion because the sigma here is not constant. It is itself a random process. And so the extreme cases of beta 0 and beta 1 are also used. They're also used, but the formulas that I'm going to give you, some of the formulas don't work unless beta is strictly between 0 and 1. I gave you some references in the homework problem, homework set 4. There's references for the most important papers about the SABRE model, and you can find the formulas for beta equals 0 and beta equals 1 in those papers. The nu here, let's see, alpha. Alpha, of course, is positive. The nu is positive. And alpha, beta, nu, and rho. In the homework, I said rho has to be between -1 and +1. In fact, as I was reading, getting ready for this lecture, I found a paper that rho has to be between -1 and 0. If rho is positive, then S is not a martingale. And this is the confession time. I've said that Ito integrals are martingales, and if you integrate this formula for S, you'll see that S is an Ito integral. It's this stuff integrated dw1, and Ito integrals are supposed to be martingales, but there has to be a condition, right? So if you look at S of t, it's going to be S of 0 plus the integral from 0 to t, sigma of u, S beta of u, dw1 of u, and in order to construct the Ito integrals, we have to have the condition that the expected value from 0 to whatever is our final time of the square of the integrand du is finite. And in fact, in this particular case, this is infinite if beta is bigger than, if rho is bigger than 0. So you can still construct the integral, but it's not a martingale. this is aggravating, and it means that you don't want to use the model with rho positive. And if you look in the original papers on Sabre, they say when we calibrate, we almost always get rho to turn out to be negative, and that's really good, because if rho ever turns out to be positive, you can't use the Sabre model. You should throw that away and try something else. In the homework, then, I give you an example of an Ito integral. It's not this one, but I give you an example of an Ito integral that's not a martingale, and you go through and verify that it's not a martingale. So you can see that that really can happen if this condition, if this expected value turns out to be infinite. We have never worried about this before, and I would prefer never to worry about it. We don't want to keep having to stop and check this condition. And it's always been, this has always been finite in all the applications that you've seen up until this point. But now we've come to a model where it's not. So I have to be honest with you and say, sometimes you can have Ito integrals that are not martingales. Okay, so these are the ways we take the parameters. And now, why is the Sabre model useful? Well, you can compute with the Sabre model, so you can compute prices, options, and other derivative securities can compute derivative security prices. With the Sabre model. By two methods. You can solve PDEs. In order to have partial differential equations, you need Markov processes, and the pair S nu is Markov. It's actually the solution to a two-dimensional stochastic differential equation. And so using all this stuff about find the martingale, take the differential, set the dt term equal to 0, that will all work. And you can get partial differential equations with boundary conditions, and you can solve them numerically. And so you can get prices that way, or by Monte Carlo. Of course, if you're doing Monte Carlo with the Sabre model, you have to have two Brownian motions. And what I would recommend is, it's always easier to work with two independent Brownian motions, but I think you know, right, how to take correlated Brownian motions apart into independent Brownian motions, is it? I see some people nodding. So you did that in stochastic calc 1, I trust. So if you have correlated Brownian motions, you decompose, say, this one into two independent Brownian motions, and then you can do a Monte Carlo simulation. But to do this, you need to know the parameter values, alpha, beta, rho, and nu. And so there's a calibration that's necessary. So, given alpha, beta, rho, nu, you can compute call prices with the model. And with a call price from the model, you can ask, what volatility would I need to plug into Black's formula in order to get Black's formula to give me the same price? And so then you can use Black's formula to buy volatilities. Okay, is that process clear? All right, so you have an expiration and a strike, and then you use Sabre, and you get a call price. And you'd like to get this with the same expiration and the same strike. You would like to use Black's formula and get the same call price, and you ask, what volatility do I use in Black's formula to produce that same price? And I'm going to call that I of, it's weird here. It's called I of x and t, and the x that shows up here is the log of s of 0 over k, or another way of saying that is that k is x e to the minus s of 0. So it turns out that it's most convenient not to let this volatility be a function of the strike and the time to maturity. It's most convenient to let it be a function of the time to maturity and a variable called x, and x and the strike are related by this equation. S0 is not a variable. S0 is just today's price, so it's a constant. And it turns out that the x is a more convenient variable to work in than the strike. X is called, so S of 0 over k is called the moneyness, and x is called the log moneyness. So x equals 0 corresponds to at the money. That's when the strike and the initial price of the asset are the same. Okay, so given a time to maturity and a strike, Sabre, and given parameters, I guess I should say that. I have to have parameters here. Then Sabre will give me a call price. Given a time to maturity, a strike, and Black needs a parameter too, namely a volatility, I want to get the same call price. So given these parameters, then I can ask what are the volatilities that go into Black's formula that will give me the same call price as Sabre. And the reason Sabre is popular is because the developers of Sabre, and Pat Hagen was primary among them, have given us a formula. Here's Hagen et al.'s formula. I h of x, so no dependence on t, is alpha over s of z to the 1 minus beta of 0, 1 plus 1/2, 1 minus beta minus lambda minus rho lambda x plus 1/12, 1 minus beta squared plus 2 minus 3 rho squared, lambda squared, x squared. You'll find this in a paper by Hagen and three or four other authors that's cited in that homework 4. And the lambda that shows up here is nu s to the 1 minus beta of 0 over alpha. I messed that up. Lambda is nu s to the 1 minus beta 0 over alpha. So approximately, if you give me the parameters, alpha, beta, rho, and nu, and you give me a strike k, and it doesn't matter what the time to maturity is, it doesn't show up in this formula. You give me a strike k, I then form this log moneyness x, and I put the parameters alpha, beta, right, they're all there. Right, there's the alpha, there's the beta, there's the rho, the nu shows up in the lambda, and the lambda's here as well, and the log moneyness x is here. There's all the parameters, and what comes out is approximately equal to the volatility that you would have to put into Black's formula to get Black's formula to give you the same price. So how do you use that? Well, you look at the call prices, and you use Black's formula, and you imply volatilities. And once you've implied volatilities, you'll see a curve like this. You'll see a curve like this. And then you try to choose your 4 parameters, alpha, beta, rho, and nu, to get this function to be a close fit to that curve, so that the implied volatility that's being put out by Saber's model agrees with the implied volatility that you see in the market quotes. So you try to get this function market vols. Notice that if you plug in 0 for x, that's the case of at the money, then these two messy terms disappear, and you get simply alpha over today's asset price to the power 1 minus beta. So alpha is going to set alpha combined with today's asset price. You want to choose to get this point, the at the money implied vol. And the 1 minus beta, how do you choose the beta? If you look in the paper by Hagen and all, they make two suggestions. One of them is you can say, well, if I fix an alpha and a beta and get today's price right for the at the money volatility, this says that as the stock price moves, the at the money volatility will move as well because of the presence of the beta. And it is the case that there is a tendency when the stock price is high that the volatility in some markets is higher, in some markets is lower, and when the stock price is lower, then in some markets you see it go one way or the other. And so you could choose the beta to try to get that to be right, and then choose the alpha as a final adjustment to get today's at the money volatility right. Hagen also says people tend to use their intuition with the beta. Beta equals 1/2 is a popular choice, and they feel like that's about right. Beta equals 0 and beta equals 1 are also popular choices depending on the markets that people are working in. And there's a formula, actually this formula works for beta equals 0 and beta equals 1. The formulas I'll show you later don't, but this formula would work in that case as well. So Hagen says the following: beta, intuition, or history, to choose it. Alpha is the overall level of implied vol. If you look at what you have here, it's a quadratic function in the x variable. This term is positive for small lambdas and rhos. The 1 minus the 1 here dominates. This term is positive. As strike increases, x goes down, right? Because x is in the denominator here. So as strike increases, x goes down. So this would go down with increasing vol. Would go down with increasing strike, and that's like the picture that we're seeing here, where the implied vol goes down with increasing strike. But it doesn't go down too far. Eventually, because of this x squared term, it'll come back. And so this will look like the picture that we're seeing here. And he argues that you want to use rho to get the skew, sort of the slope right, and use nu, which shows up in the lambda, to get the curvature, the smile. As I look at this quadratic, it's not clear to me that that's exactly right. But I can see that you can use these 4 parameters and this quadratic function of x, and you could try to fit a smile. And Hagen has, and others have lots of pictures where they've taken this model to different markets, and they've fit the implied volatility smile, and it fits very well. Okay, so by that device, you choose these 4 parameters, and now you're on your way. You've got a model, and you can start to compute prices of derivative securities with it. As I said, you can do that either by Monte Carlo or by solving partial differential equations. And there's a third way to compute prices. Of vanilla options, something that's not path dependent. And that third way is that there's a formula that is considerably more accurate than this. This is an approximation to the implied vol that the Sabre model produces, but there's a formula that's considerably more accurate than this. In fact, it's so accurate that you could use that formula to get the prices that the vanilla calls that the model produces. What I'm saying is that once I tell you the strike and the maturity, you take the formula and see what is the implied vol that the formula produces. You stick that into Black's model, and that'll produce a price. And that formula, I'll write it down for you. It's not nice, but here it is. So this is the more approximate, more accurate formula for implied vols. In Sabre. I'm getting this from the paper that's in the references by Obloy. So there are two parts to it. There's an I0 of x, which looks like nu x over log z minus rho plus square root 1 minus 2 rho z plus z squared over 1 minus rho, and the z that shows up here is nu s to the 1 minus beta minus k to the 1 minus beta. This s is s0 over alpha to the 1 minus beta. And there's another function, I1 of x, hang on, alpha squared, beta minus 1 squared, 24, sk to the 1 minus beta plus rho nu alpha beta over 4 sk 1 minus beta over 2 plus 2 minus 3 rho squared nu squared over 24, and then the implied volatility, which is a function of x and t, is I0 of x 1 plus I1 of x times t. So this is an accurate approximation to implied volatility produced by the Sabre model. And so accurate that except in cases of small capital T's and large X's, you could actually use this to produce option prices. If what you're pricing is just vanilla calls and puts, you could use this formula and plug the implied volatility that it produces into Black's formula and get the prices out. Okay. So what I wanted to say here was there are many models. Sabre is particularly popular in fixed income, and I wanted to make sure you have some idea of how one deals with the case of non-constant volatilities, because they're not. And they're not constant, right? And the days of using constant volatilities are over, and one has to do more sophisticated things. And Sabre is one of the simpler, more sophisticated things that you could do.
Professor?
Yes.
I have a quick question. So just to verify how you can use the implied volatility to get prices, you said you would find the volatility from Black's formula and then set that volatility equal to I and then solve for X, and then once you know X, you know price. Is that correct?
So let me, so you're asking about this last step here?
Yeah, how do you get a price from I?
So
I is trying to get a volatility, not the price, right?
Yeah, so what I do is once I have my Sabre model, and so I know all the parameters, and notice that there's a little oddness here. I've written this as a function of x, but k's show up in it, but k is a function of x, right? So k is a function of x here. So I've written this as a function of x. once I have all my parameters in the Sabre model, and then you give me a particular call, it has a time to expiration and a strike, a T and a K. And so I take the K and get the X from the K according to this formula, right? And then I compute this function. And I use that as the volatility in Black's formula. And that produces a price for the call. Okay, so I take this and plug it into Black's formula, and that produces the price for the call. And it works well, except, as you can see, this is a very complicated function. And I gave you a homework in which this function was just x squared, just to give you a feel for it. And the same thing happens in your homework as happens with this very complicated function, which is that it works well until it doesn't work. So for small values of capital T and large values of x, this approximation is not good. This one's not good, and the one in your homework is also not good. And the way you discover it's not good is that when you check what is the risk-neutral distribution that goes with it, you discover there is none. It has negative values, and so it can't be a probability density function. But except for those cases, this produces good prices. It's close to the prices that the model itself would produce. The model, of course, is arbitrage free. If I write down this model and compute accurately with it the prices of vanilla calls, I will get prices that are free of arbitrage because I have a risk-neutral measure. In fact, in this case, the forward measure is the risk-neutral measure. It makes all the asset prices be martingales and no discounting is involved. And so this is arbitrage free. And if I can compute accurately the prices that this model is giving, then I don't need to worry about arbitrage. This will produce accurately, this method will produce accurately those prices, except in the cases of small maturities, small expirations, large moneyness, large X. Have I answered your question?
Yep, thanks.
Sabre is a complex model, and a particularly simple case of Sabre that actually was invented before Sabre was the case where nu equals 0. And that's CEV, so that's constant elasticity of variance. I don't know quite. This was named by people in finance, and I never quite know why they come up with these names. I guess it's because I don't have a good economics training. So here I said that nu is positive, but if we take nu to be 0, it means that the volatility term, the differential of sigma, is 0, and so sigma is just a constant equal to its initial condition alpha, and so then we get only a one-dimensional equation. This is just alpha S beta of t dw1 of t. And now we have only two parameters to worry with, alpha and beta. And everything I said about Sabre still applies. There are formulas. In fact, you can take Hagen's formula. You can take Hagen's formula here, and you can set nu equal to 0. If you set nu equal to 0, then lambda is 0, and the formula simplifies considerably, and that will give you a good approximation to the implied volatility surface that is going to come out of the CEV model. And you can then try to choose your parameters alpha and beta so that that implied volatility that comes out of this formula is a good fit to what you see in the market. And then once you've got the alpha and beta, this is an arbitrage-free model. And then you can do pricing using this model. And there are two ways to compute prices. One is solving partial differential equations. Now it's only one-dimensional. Monte Carlo, again, it's only one-dimensional. And if you're pricing vanilla calls, you could use this third method where you have a function like this, and you could use the implied volatility that this function generates and just plug it into Black's formula. the formula for the case when nu equals 0 is not the one that you don't get it by setting nu equal to 0 in this. But if you look at O'Boy's paper, he gives you the formula when nu equals 0. And so again, you have the three methods, and the same thing goes. And the only case that you have to be careful of is that if beta is bigger than 1, S is not a martingale. And for homework, you verify that for the case beta equals 2. Okay. You will not be required to remember these formulas. I would like for you to know the concept. You know, what is it that's going on here? How are we using implied volatilities? What is the concept by which we calibrate these models? Right? But you're not going to be asked to remember any formulas. Okay, let me see if there's a question.
Yeah, Professor, I have a question.
Yes.
So this class we talk about the black formula. So what's the advantage of the black formula over the Black-Scholes formula?
So the question is, what's the advantage of the black formula over the Black-Scholes formula? The black formula is almost universal in fixed income markets, because in fixed income markets, it doesn't make any sense to build a model unless the interest rate is random. And when the interest rate is random, we have this problem of pricing calls where we have to worry about the correlation between the discount. Right? So when the interest rate is random and you're trying to price a call, you have to worry about the correlation between the discount process and the underlying asset process. And that's a hard thing to worry about. And so we deal with that by changing the measure. And then we wind up with Black's formula instead of Black-Scholes. If you're doing equity derivatives rather than fixed income derivatives, then you would typically be using a constant interest rate. You would be using Black-Scholes. You would do everything that I've just described, but you'd be using Black-Scholes rather than Black to imply the volatilities and all of that. Any other question? So the third topic of the evening I want to talk about is foreign exchange, but I promised you guys 2 breaks, and it's been a short period, but I think we should take our second break since I'm going to start a new topic and I'd like for you to be fresh. So why don't we take another, well, let's this time take a short break. I won't leave the room, so I'm sure that we'll get started on time, and I will return homeworks. Let's take a 10-minute break. So I'll tell you what, let me deal with questions after class tonight. And oh, okay. Okay, why don't we wind up? I had remembered that I had made a promise to the afternoon class yesterday that for this business about in the Sabre model, if the correlation rho is positive, that the underlying asset price is not a martingale. This is the one reference that was not in that homework, and so I've written it down here. So it'll be on the lecture notes when they go up on the website, if you're interested in looking at the reference on that. So I'd like to conclude then with a discussion of foreign exchange. I'm going to write down the simplest model I can that is rich enough to see something. And so we're going to take two Brownian motions, W1 and W2, independent Brownian motions. Under the actual measure P. And I'm going to have a stock. So ds of t is a constant alpha s of t dt plus a constant volatility sigma 1 of s of t dw1 of t. I'm going to have an interest rate R, a domestic interest rate. Then we'll have a domestic money market account. Which would just be e to the RT. So you take $1, you put it in the money market, and it grows continuously compounding at the rate R. So by time t, it's e to the RT. And I will use the notation 1 over d of t for that. So d of t is as usual, is a discount process. We could make a richer model that I'm making here. In particular, we could let the interest rate R be random. If you were going to do that, then you would want to put in more Brownian motions. And as I say, I'm trying to build the simplest one in which we can see something interesting happening. So I'm going to just leave R constant. We also have a foreign money market account. And e to the RFT, where RF is the foreign interest rate. And I'll use the notation 1 over df of t. So df of t will be the foreign discount process. And I don't know. Let's let domestic be dollars and foreign be euros, so that I don't have to keep saying foreign and domestic. I can just write dollars and euros as we go through this calculation. And we have an exchange rate. X of t. And this is the dollar price of a euro. So that will vary with time. And the model we'll write down for that is dx of t. We'll write a geometric Brownian motion gamma x of t dt plus sigma 2 x of t. And then I want to put in a correlated Brownian motion here. So I'll write rho dw1 of t plus square root 1 minus rho squared dw2 of t. I could just as well have said W3 of t, which in this case would be rho W1 of t plus 1 minus rho squared dW2 of t. And then here I could have written dW3 of t. W3 is a Brownian motion. You can check with Levy's theorem, and it's correlated with W1. So the whole point of this is just to build in some correlation between the stock and the exchange rate, but I've explicitly indicated here what is the same Brownian motion that drives the stock, and then what is the independent piece. You can build exchange rates that are mean reverting. You can build exchange rates, foreign money market accounts where the foreign interest rate is random. So you can soup this up in many ways. But what we're most interested in is how we move back and forth between the risk neutral measures in the two countries. And we can see that in the simple model. So let's first of all find the dollar risk neutral measure. And what I mean by the dollar risk neutral measure, it makes dollar prices of assets discounted at the dollar interest rate be market deals. So for example, if we take this stock and we discount it, I would multiply it by D of t. Right, so that's e to the minus RT S of t. And we want that to be a martingale. If I take its differential, and now I'm just going to quit writing t's because it's 10 minutes till sometime 8. And we have some distance to go, so we'll just leave the t's out. ds, what happens here? Well, if you discount, the mean rate of return is alpha under the actual measure. The mean rate of return will be alpha minus r if we discount. And then instead of stock, I'll see discounted stock. But the volatility term will be unaffected except for the fact that stock will get discounted. Okay, so there's discounted stock. And what we would like to see is we would like to see no dt term because we want a martingale. And where we see dw1, we'd like to see dw1 tilde. So we'd like to see sigma 1 ds. And then what does dw1 tilde look like? It looks like some theta 1 dt plus dw1. Right, this will be the dw1 tilde. And in order to get that to work, the thing that multiplies the dt up here, which is an alpha minus r times discounted stock, has to be the thing that multiplies dt down here, which is sigma 1 theta 1 times discounted stock. And so we have a market price of risk equation. We're going to have to choose theta 1 to satisfy this equation. And the theta 1 we use both to change the Brownian motion, as indicated here, from W1 to W1 tilde. And we also will use the theta 1 in the Gersanoff theorem to create the Radon-Nikodym derivative to move us to the other asset, the other measure. But we have two Brownian motions in this model because we have an exchange rate and a second Brownian motion is involved in that. And so we're going to need to find another market price of risk, a theta 2, to go with the second Brownian motion. So we need to think of another asset that we can denominate in dollars and discount at the US interest rate and make it be a martingale. And the other asset, if you think about it, is a unit of foreign currency. I buy a pound, and then I just keep pricing it in how many dollars is it worth. And that looks like another asset to me. But of course, if I buy a pound, I'm not just going to sit on it. I'm going to invest it in the foreign money market account. So the other asset is I buy a pound and I put it in the foreign money market account, and it grows at the foreign interest rate. But I want to price it in dollars, and this is pricing in pound. I'm sorry, I switched somewhere from euros to pounds, didn't I? Let's do euros. Euros is enough foreign. We don't have to talk about pounds. So I buy a euro. I put it in the, Lord only knows what the interest rate is there. I put it in a money, I give it to the European Central Bank. I put it in a money market account. It's growing at interest rate RF, but I want to compute its dollar price. So I multiply it by the exchange rate to get the dollar price. And so this is denominated in dollars. And I could also write this as x of t over df of t. Right? 1 over df of t is rf, e to the rf of t. And I want it discounted to be a martingale. So I want to look at the discounted x of t over df of t. So without actually doing all the calculations, let me just talk my way through. The mean rate of growth on the exchange rate is gamma. If I discount it at the U.S. interest rate, that will reduce the mean rate of return by R. Here I am inflating it at the foreign interest rate, right? I'm inflating it at the foreign interest rate. That will give it an increase at rate RF. And so what we're going to get here is gamma minus R plus RF x dt. I'm sorry, it's not x, it's dx over df dt. And the volatility structure stays the same, so we get a sigma. X is now become dx over df. And then we have rho dw1 plus square root 1 minus rho squared dw2. And what we would like to see is no dt term. So we would like to see sigma 2 dx over df rho. And then, of course, we can get, instead of dw1, we'll have a dw1 tilde. And that will look like theta 1 dt plus dw1. And then square root 1 minus rho squared. And instead of w2, we'll have a dw2 tilde. And that will look like theta 2 dt plus dw2. This will be our dw1 tilde. And this will be our dw2 tilde. And in order to get that to work, the thing that multiplied dt in this line has to be the same that multiplies dt in this line. The thing that multiplies dw1 and dw2 are obviously the same in the two lines, but we have to get the dt terms to be the same. The dt term in this line, if I ignore the dx over df, the dt term in this line is gamma minus r plus rf. And the dt term in this line, again, ignoring the dx over df, is sigma 2 rho theta 1 and sigma 2 square root of 1 minus rho squared theta 2. And so there's a second market price of risk equation. And we solve these two equations for theta 1 and theta 2. And you can do that unless there's some degeneracy. If you think about what's going to happen, well, first of all, here you're going to have to divide by sigma 1. So you don't want sigma 1 to be 0. But if sigma 1 is 0, sigma 1 is the volatility of the stock. If sigma 1 is 0, the stock has no volatility, and it's like a second money market account. And either it's the same money market account that you already have, in which case that's redundant, or else it's a different money market account, in which case there's an arbitrage, right? And likewise, you're going to need to divide, to solve for theta 2, you're going to need to divide by sigma 2. Sigma 2 is actually the volatility of the exchange rate, and you want it to have a positive volatility, or else this is a dumb model. And you also have to multiply by square root of 1 minus rho squared. If rho is either plus or minus 1, there's perfect correlation between the exchange rate and the stock, and that's also a dumb model. In all of those cases of the dumb models, either you're going to have an arbitrage or you're going to have multiple risk neutral measures. We're going to assume that we can uniquely solve these equations so that we know that we have a complete model and we have a risk neutral measure, and we move on. So let's assume there's a unique solution. Then we can define the domestic risk neutral measure P tilde by saying that its Radon Nikodym derivative with respect to P is minus theta 1 W1 of T minus theta 2 W2 of T minus 1/2 theta 1 squared plus theta 2 squared times T. That's Kirsanov. And if we do that, then W1 tilde of T defined to be theta 1T plus W of T, W1 of T, and W2 tilde of T defined to be theta 2T plus W2 of T are independent Brownian motions under P. And we have the following model, following formulas. Let's just write the discounted stock price here. The differential of the discounted stock price is, I'm just copying this formula down, sigma 1 ds dw1 tilde. And the differential of this thing, it's discounted x over df, is sigma 2 discounted x over df rho dw1 tilde plus square root 1 minus rho squared dw2 tilde. Okay, discounted asset prices are now martingales under P tilde. If we look at their undiscounted versions, so if I just take the differential of S instead of ds, then what will happen is that I'll see this interest rate pop back up. We'll get an RSDT, and then I'll get a sigma 1 S dw1 tilde. Okay, so it's like where we started, except now that's an R rather than an alpha. And if I take the differential of x over df rather than discounted x over df, then the same thing will happen. An R will pop up. I'll have an x over df dt, and then I'll have a sigma 2 x over df, and then I'll have rho dw1 tilde plus square root 1 minus rho squared dw2 tilde. Is everybody okay with going back like that? If you have this, you use a product rule. You multiply this by e to the plus RT, because this d is an e to the minus RT. So you multiply by e to the plus, RT, take the differential using the product rule, and you'll go back to this equation. And the same thing here, multiply by e to the plus RT, use the product rule, and you'll come up with this equation. But what's happening is sort of natural. When I multiply by e to the plus RT, I introduce a rate of growth R, and I cancel this d term that's on the right-hand side, so you don't see it anymore on the right-hand side. This df that's sitting here in the denominator is really an inflationary term, right? The df in the denominator is really an e to the RFT multiplying x. If I take it away, I'll reduce the rate of return on x. And so if I write this one without the df, then instead of r here, I'll get r minus rf. Sigma 2 x rho dw1 tilde plus square root 1 minus rho squared dw2 tilde. Where have we seen an equation like that before, where the mean rate of return is not r, but r minus something under the risk-neutral measure? A dividend-paying stock, right? So the exchange rate is looking just like a dividend-paying stock. The dividend is being paid out to the constant rate equal to the foreign money market rate, right? Which is exactly right. If you own a unit of the foreign currency, you're getting a dividend from investing it in the foreign money market account. And if you were to write down the price of a call on the foreign currency, right? If I want to price a call on a euro in dollars, I'd get the Garmin-Cohagen formula, the same formula that we got for dividend-paying stock. That was actually where they first developed it in the context of foreign exchange. Okay, so if we're going to go the full Monty here, we have to think about the foreign risk-neutral measure and the foreign Brownian motions. If it's quiet in the hallway, maybe you can just leave that door open and we can... It's probably quieter in the hallway than it is outside. So we want to change to the foreign risk-neutral measure. Why do I call this one the domestic risk-neutral measure? It's because this is the one that took the asset prices in dollars, discounted at the domestic interest rate, and made them be martingales. The foreign risk-neutral measure would take the prices of the assets denominated in euros, discounted at the foreign interest rate, and make them be martingales. And so how do we get to that? So we want to change to the foreign risk-neutral measure. And now I'm going to give you my best attempt to explain this in a way that doesn't cause everybody's brain to explode. So we have here three assets. We have a domestic money market. We have a stock. And we have a foreign money market. We have four ways of denominating these assets. We could denominate them in dollars. And when I denominate in dollars, the price of the stock is S of T. The domestic money market is E to the RT, which I'm writing as 1 over D of T. And the foreign money market is E to the RFT times X of T, right? It's the foreign money market converted to dollars, or that's also X of T over DF of T. I can also denominate in units of the domestic money market, which is a fancy way of saying discount. So I'm going to divide everything through by the price of the domestic money market account, E to the RT. So this becomes a 1. This becomes a discounted S. And this becomes a discounted X over DF. And under the risk-neutral measure that we've constructed, the domestic risk-neutral measure, this is where we have the martingales, right? Discounted S is a martingale under the measure that makes W tilde be a Brownian motion, and discounted X over DF is a martingale under the measure that makes W1 tilde and W2 tilde be a Brownian motion. So this line is where we have the P tilde martingales. And I'll remind you again about what this business of finding risk-neutral measures is all about. We want to make all the assets be martingales so that when we form a portfolio, we know that our portfolio is a martingale. We don't make the dollar prices of the assets be martingales. How do you make an asset be a martingale? Well, you look at a price process, and there's some paths that go up and there's some paths that go down. And if it's on average going up, that means you've got too much probability on the up paths. If you want to make it be a martingale, you put less probability on the up paths and more probability on the down paths. And so you pull down the mean return. And that's how we make things be martingales. That's what your Sarnoff's theorem is doing. But if you look at the domestic money market, it only has one path, and it's up, e to the RT. And there's no way to change the measure and make that money market be a martingale because there's no down path that you can put more probability on. And so what we do is we first discount. We divide everything by the price of the domestic money market. And then in units of domestic money market, this one becomes a 1. That's a martingale. The one path we have is just a flat 1, and that's a martingale. And then we change the measure and make these two be martingales as well. And so we get all three in this row to be martingales. And then we know that any portfolio that we form would also be a martingale if we price it in units of domestic money market. We can also price in euros. And so to get euro prices from dollar prices, I just divide by x, right? Multiply by x to go from euros to dollars, divide by x to go from dollars to euros. So I just divide by x. So here I have 1 over d of t x of t. Here I have s of t over x of t. I'm dividing the top row by x. And here I have e to the rf t, which is 1 over df of t. And now we have the same problem that we cannot change measure and make all of the entries in this row be a martingale because the last entry only has one path and it's up. And we don't have any down path to put more measure on. And so what we're going to do is we're going to take this foreign money market as our numeraire. We're going to price everything in units of the foreign money market. And that's really discounting at the foreign interest rate. So we're pricing in units of the foreign money market. And this now becomes a 1. And here we discount at the foreign interest rate, df of t, s of t over x of t. And here we have df of t over d of t, x of t. And so we want to find the foreign risk-neutral measure. I'll call it P tilde of F. So these are martingales. Okay, so are you happy with my table? The next observation is that, so this was easily a martingale. Just a flat 1 is always a martingale. But these two we have to think about. And the way I'm going to think about them is I'm going to say these are quotients of martingales. In fact, if you take this entry and this entry, which are martingales under P tilde, and divide them by the last entry, which is a martingale under P tilde, you'll get this entry. Right? So what I'm saying is this entry right here is that 1 divided by the last element. Right? And this entry is this d of t s of t divided by the last entry in that line. So here's the numeraire. Right? I'm going to price everything in units of that. I'm going to price these two in units of that. So the Radon-Nikodym derivative process to go from P tilde to P tilde of F is d of t x of t over df of t. That's already a martingale under P tilde, so I don't need to, right, it's already been discounted, but I do need to normalize it so that it has expected value 1, so I have to divide it by x of 0. So it's that product. The volatility vector of the numeraire there it is, right? It's dx over df. Dividing it by its initial condition doesn't change the volatility. And the volatility, we see it here. The first Brownian motion is being multiplied by sigma 2 rho. And the second Brownian motion is being multiplied by sigma 2 square root 1 minus rho squared. So, do you remember how we get the foreign Brownian motions? You take the Brownian motions we had, and you subtract off the volatility vector times time, right? So this will be minus sigma 2 rho times time. W2 tilde of t minus sigma 2 square root 1 minus rho squared times t. And whenever you're trying to change the probability measure, right, you're going to use this as the Radon-Nikodym derivative. What happens to what is the volatility of S in euros? Well, how would I think about that? Right, so that's, what is that? That's the volatility of this term right here, right? I'm trying to, i.e., the volatility of, it doesn't matter whether I write here S over X or DFS over X, because the DF is just exponential growth. There's no volatility in that. So the volatility of this with the DF or without the DF, it will be the same. And how do we get the volatility? Well, this, I think of this as a quotient. Let me put the DF in. It's a quotient of martingales. What's the volatility of the numerator? Vector of the numerator, where is ds? There it is. It's a sigma 1 multiplying the first Brownian motion and a 0 multiplying the second Brownian motion. We've already seen the volatility vector of the denominator. That's right here. And so the volatility vector of the quotient, this term, volatility vector subtract, right? Sigma 1 minus sigma 2 rho, 0 minus sigma 2 square root 1 minus rho squared. the trading floor volatility, right? I'll call it the traditional volatility. This is the S in euros is. It's the Euclidean norm of this. Sigma 1 minus sigma 2 rho squared plus sigma 2 squared 1 minus rho squared square root. And you can work that out a little bit more. It's a sigma 1 squared minus 2 rho sigma 1 sigma 2 plus sigma 2 squared rho squared plus sigma 2 squared minus sigma 2 squared rho squared square root. And something should cancel this. Right, so it's sigma 1 squared minus 2 rho sigma 1 sigma 2 plus sigma 2 squared. If you think about that, maybe it makes sense to you. Sigma 1 is the volatility of the stock when we denominate it in dollars. Sigma 2 is the volatility of euros when we denominate them in dollars. Rho is the correlation between the stock price and the euro price. If we denominate the stock in euros, then we get this as a volatility for the stock denominated in euros. You can do all these things with Ito's formulas, right? But we did it once generically. Right? So you could actually just write down what is the differential of this thing. I'm sorry, what is the differential of this thing? And you can see what its volatility vector is. But we don't really have to do that calculation because we know that it's a quotient of martingales, and we know that its volatility vector is going to be the difference of the volatility vectors, and its traditional volatility is going to be the Euclidean norm of its volatility vector. We can do the same thing for the money market. This one is also, right, the money market here. When we're pricing in dollars, the money market has no volatility. But when we're pricing in euros, the money market has a volatility because of the exchange rate risk, right? This is the U.S. money market priced in euros has a volatility because of the exchange rate risk. And we can figure out what is its volatility vector as well. So let's do the volatility vector of the domestic money market. Well, the numerator is just a 1, so it has no volatility. And the denominator that's the dx over df, and that's the one that has volatility sigma 2 rho multiplying the first Brownian motion and sigma 2 square root 1 minus rho squared multiplying the second Brownian motion. So the difference is minus sigma 2 rho minus sigma 2 square root 1 minus rho squared, and the Euclidean norm is sigma 2 squared rho squared plus sigma 2 squared 1 minus rho squared square root, which turns out to be the square root of sigma 2 squared, which is just sigma 2. And that seems right? This is actually the volatility of the exchange rate. And that's the only source of uncertainty in this because there's, the numerator has no volatility. So let's do a couple of things with this. Well, at least one thing, maybe two. So we had a formula for the exchange rate. here it is. The differential of the exchange rate. Let me pull it down where so you can see it. Differential of the exchange rate. R minus RF x dt plus sigma 2x rho dw1 tilde plus square root 1 minus rho squared dw2 tilde. And we said, well, that makes sense because the exchange rate is like a dividend-paying stock, and the dividend rate is this foreign money market rate. So it would make sense also then that if I look at the reciprocal of the exchange rate, so x is the dollar price of euros and 1 over x is the euro price of dollars, that we should see this same kind of term, but the interest rate should be in the other direction, right? And so let's compute that. So Ito's formula says if you take the differential of 1 over x, the first derivative of 1 over x is minus 1 over x squared, and that'll multiply dx, and then you get a half. The second derivative is 2 over x cubed, and that will multiply dx dx. So what happens here? When I have a 1 over x squared and multiplied by dx, in the dx there's an x in both terms, and so the x squared will actually become 1 over x. So what I have here is minus 1 over x r minus rf dt and minus 1 over x sigma squared rho dw1 tilde plus square root 1 minus rho squared dw2 tilde. And that looks pretty good because the dt term here is, well, instead of an x, we now have a 1 over x. And instead of an r minus rf, because of this minus sign, we now have it in the other order, rf minus r. So that looks great. But I'm not done yet because I have a dx dx here. The 2 cancels. Dx dx, when you do dx dx, you're going to have to square this out. When you do that, you'll get an x squared. The x squared will combine with the x cubed in the denominator and give you a 1 over x. And then you'll square this out, and you'll get a sigma 2 squared rho squared dt. The Brownian motions are independent. You don't get a cross term. You'll get a sigma 2 squared 1 minus rho squared dt. So when all the dust settles, here we have rf minus r in the other order as we wished, 1 over x dt. So 1 over x has mean rate of return rf minus r if we had only that term. Then we have minus sigma 2, 1 over x, rho dw1 tilde, plus square root 1 minus rho squared, dw2 tilde. So that looks good. But then we have 1 over x, and this all adds up to a sigma squared, right? The sigma squared rho squared, sigma 2 squared rho squared gets canceled. I have sigma 2 squared dt. So why didn't we expect it?
Because the Brownian motions are not Brownian motions under the foreign currency.
I'm still using the dollar Brownian motions, and I should be using the euro Brownian motions, right? So right here, where you see dw1 tilde, dw1 tilde is, according to this formula, is dw1 tilde f plus sigma 2 rho dt, and dw2 tilde is dw2 tilde f plus sigma 2 square root 1 minus rho squared dt. And if you put that in, then this term will go away. You can sort of see it happening right here. right? This row will multiply this sigma 2 row and give me a sigma 2 row squared. This will multiply that and give me a 1 minus rho squared. Ultimately, a sigma 2 is going, dt is going to come out of here, and it's going to be multiplied by that sigma 2, and it will have a minus sign. And so if you finish the algebra here, you'll get rf minus r, 1 over x dt, and then you'll get a sigma 2, 1 over x, rho dw1 tilde of f, plus square root 1 minus rho squared dw2 tilde of f, right? It's time to quit, but I want to write down one more thing that shows you the change of measure. So that was an exercise where you have to remember to change the Brownian motions. Let me show you an exercise where you have to remember to change the measure. I'd like to think about forward exchange rates. So let's think about the following problem. I'd like to lock in a forward price for a euro. So at time capital T, this is how many dollars a euro will be worth. I'd like to lock in a forward price at time 0. And the way forward price is chosen is so the value of this payment at time 0 is 0. And so how do I compute the value of that payment? I discount it at the domestic interest rate and take its risk-neutral expected value under the domestic risk-neutral measure and set that equal to 0. So let's take this apart. The first term is E tilde d of t x of t. And in this particular case, d of t is not even random. So d of t is just e to the minus rt. So I can take it out, and this is not random. But the problem is that this is not a martingale under the domestic risk-neutral measure. If you look at what is the martingale under the domestic risk-neutral measure, it's this. So I have to divide and multiply by df here to get a martingale. So if I divide by df and multiply by df, and I can do this because these discounts are not random in this case, then I have a martingale right here. And so this is equal to its initial condition, which is x of 0. And then I can solve for the forward exchange rate. So I get e to the minus rt. Forward exchange rate is equal to df of t x of 0, which is e to the minus rf of t x of 0. And so forward exchange rate is e to the r minus rf times t times x of 0. Okay? Let's do it the other way around. So if I'm sitting in Europe and I want to lock in a price for $1, so there's the price for $1. This is the euro price for $1 at time capital T. I want to lock that in at time 0, so I'll call this the forward price for the exchange rate in the other direction at 0t. We want to discount that at the foreign interest rate and take its expected value under the foreign risk-neutral measure and get 0. So there are a couple of ways that I can do this, but the way I want to do it is I want to change the measure. Okay, this is the point of the exercise, to show you a case where you change the measure. So this thing I could write as an expected value under the domestic risk neutral measure if I multiply by the Radon-Nikodym derivative, which is d of capital T, x of capital T, x of 0, df of capital T. And the thing I'm multiplying here is this. Df of capital T, 1 over x of capital T. The other term is not random, so I'm not going to worry about it, right? This is not random. This is just e to the rf capital T, and this is not random. So I can take it out of the expected value. It's the first term that's random that I have to worry about. And then what happens? Well, cancellation. This cancels this. This cancels this. And so this is easy to compute. This is d of t is e to the minus rt, and then a 1 over x of 0. And then minus this, e to the rft, forward 1 over x 0t is 0. And if we solve this equation for the forward exchange rate, well, I'm going to get fouled up. No, something went wrong here. Let me see. Oh, I know what went wrong. df of t is minus rf. So this is minus. And so when I solve this for the forward exchange rate, I'll get E rf minus r times t 1 over x of 0, which should be the reciprocal of what we had before, right? So that seems good. Okay, I just wanted to give you one example in which you use the Radon-Nikodym to change from one measure to the other when doing the calculation. All right, out of time and then some. Let me see if there are any parting questions. Next week we're going to do the Heath-Jarrell-Morton model. So we're done with change of numeraire for a while at least. And we'll go back to the HJM model, which is one of the classic models of term structure of interest rates that you should all know. Any questions to wind up? Okay, I'll see you in New York. I'll be there next week. I'll come in early enough that I can have some office hours in case you have some questions.